Earlier this week, we talked about machine learning. For supervised learning, where basically we need to provide, as Ramona said, we had to provide not just the picture, the data, but we have to even tell it what is it supposed to be looking for. And it requires a lot of effort. I never thought I'd be labeling so much. So when I first started this, I was like, okay, I'm labeling 300. That's the only time I'll label. No, I found I was labeling quite a bit since then. So as much as how cool machine learning and supervised learning is, there's a side to it where there is work to be done. And if you guys ever invent a way that auto labels, man, I'm gonna come to you and you're gonna make a lot of money. Do you think most learning is done on unsupervised learning, machine learning then, if you don't have to tell it the truth or not? So the question's here to pose as to get you guys thinking about what actually happens out there. I tried to find the answer on the internet and I struggled with this, but one thing to distinctly point out about supervised versus unsupervised, they do serve two different use cases in that if I have the data and I know the truth and I know what it's supposed to be, I can give it to the machine learning. Whereas for unsupervised, if I'm not even sure yet what that is, I might want to pick out some things, and it helps part of identifying anomalies, like unique situations. So just to gloss over, unsupervised machine learning algorithms learn from data that contains only inputs. We're not labeling them. So in step one, we're providing a lot of data. Step two, we're gonna provide it some algorithm, and there's a lot of different algorithms for unsupervised learning. And it's gonna find some like hidden relation or based on the input data. So you might throw a lot of data at it, and it might say, hey, we see a group of people that tend to eat a lot more hamburgers versus, oh, there's another group of people that just eats pizza. Sorry, that's a cheesy example, but it's used to definitely group things together and look for unique situations where data points relate to each other. And some of those type of algorithms that we'll go over are k-means, principal component analysis, anomaly detection, and there's a ton more. There's so many that it would probably require like a whole week just to go through all of them. But we'll just talk about some of them. So imagine yourself at a company, and this is Mike worked at a company called Grab, which was basically the Uber of Southeast Asia. And in his team, he had to discover trends and patterns from data that they were collecting to improve business and serve their customers. So what kind of data do you think that, let's just imagine if you're in an Uber company, everyone knows Uber, right? What do you think the type of data that they're collecting? Like you put in Uber, you have an Uber app, you're hailing for a ride. What do you think is the type of information Uber is collecting from you? Let's say I hail Uber. Someone picks up the request, right? Like someone who's driving, and it takes them, say, I don't know, 10 minutes to get from wherever they are to picking you up. Would you imagine that they're tracking how long it takes for the person from the moment that they accept the request to the moment that they pick you up? They're probably tracking the amount it takes for them to pick you up. Imagine what other kind of data that they're picking up. Kind of more specific to what would you care about if you were taking a ride service?
Maybe like if the driver is driving, like if they're driving fast, or maybe if it's like how long it actually takes, like for them, like the traffic and all that. I don't know.
Okay, someone else was going to say something. So this is just to say they're collecting a ton of information. Those are the things you can see for the most part. There are other things you can't even see that they're collecting, but we'll talk about that at some other point in time. And so, for example, one data that we talked about is like what kind of drivers are out there, whether it's based on, how fast they're driving or if they're responsive or, their rating. And likewise, you give a review, the driver is also going to give a review on you. So they're gonna say, oh, this customer was rude, they were snotty, or this customer is awesome, this person tips me and talks to me as a regular human being. So those type of data is being collected. So when you have all that data, and for the company of Grab, that like all these type of companies, they have teams that use unsupervised data to discover those type of relationships and structures. So how would you go about looking at that data? So remember, in some of the earlier classes, we talked about exploring your data. You kind of like load your data in and you just try to figure out what's in your data. Like who remembers pandas? Like the COVID-19 data that you guys pulled or from the US Census. You're like, you look at it, you're just like, okay, oh, there's this rate thing, there's how many people have made more than a medium income, data like that. And so you start looking at that and start thinking about, okay, well, what kind of things can we build here? What kind of features can we like pull from it? And then based on what you think, you're using some of your intuition based on your understanding of the core relationship or relationships between the different data, even if they're from different data sets, and you're building features. And then with those features, you're applying one of these unsupervised learning algorithms. And in the case of partitioning, you're like trying to discover groupings. Now, remember, correlation does not mean causation, meaning that it's not directly related, but there's a tendency for some things to occur with another. So they're looking for those type of situations and patterns. Now, for example, let's say you're in like a rideshare service again company, and you have now your little groups of data that you've built from um, exploring and running your unsupervised machine learning algorithm. And then from there, you can see, okay, we're going to have this new driver sign up with our company and add to our system. And based on the data that they're producing, they'll automatically be categorized in one group or another. So what's interesting, they'll find a lot of interesting things going on here, trends, or oh, people tend to like to do short rides, and this particular driver tends to do it. Then they can kind of try to map out, how to optimize the system for more efficiency. Or in some cases, and this happens in a lot of places, is they're looking for patterns and they'll see, hey, these people aren't really paying. They're trying to fraud the system or game the system, and they'll detect them in a particular group or cluster when they're using unsupervised learning. I'll give you one situation in my previous line of work. There are people in the basement that that process cash. So you guys probably don't touch paper money anymore, do you? Dollar bills, five bills. So those type of notes, they end up either at banks or whatever, but they ultimately end up at a bigger bank. And in the basement, they have these machines where they run this money through. And it's tons of money that goes through these big machines. And what they noticed that is they put in, let's say, $1 million through the machine, but for some reason they're getting like maybe $999,995 coming out. And what they used is they used unsupervised learning to find, hey, there's money keeps disappearing with this particular team of people. And they were able to deduce from that unsupervised learning algorithm to help them find that pattern, to find that someone was actually pocketing the money while they were processing money. So things like that you can detect using unsupervised machine learning, which I actually know they used last year. So other applications, there's something called market segmentation. I'm not sure if any of you have taken marketing yet, but when you look at, if I want to sell iPhone, right? How many different types of iPhone there are right now? Like you got iPhone, what, 11, you got the iPhone 11s, you got the iPhone Pro. There's a lot of different ones, right? Why do you think Apple made so many different types of iPhones? Yeah, so they're collecting data on people's preferences, or maybe the size of people's hands on average, or they're using some distribution and they're getting feedback. And they'll use things like that to kind of figure out what your potential market segments are. Like I would never imagine that they would bring back a smaller phone, but there was a need for it. Other things may be trying to, like in Facebook, they're trying to figure out, what social groups that are being formed, and they try to target ads that way. Or um, imagine all the computers and services that you're using. You don't know this, but all your apps go to some big server out there, and that server sits in a big data center. And in that data center, these are huge data centers. If you were to walk into a data center, you don't know which app is running on which server, but what they're collecting is the usage of power, the usage of input output transfer rates. They're collecting tons of data to figure out how to best optimize. Like, oh, this particular area, the server of the data center is getting super hot. Okay, we're going to turn on the AC fans there. Or they say, okay, maybe we can't just turn on the AC fans. If it's so hot there, maybe there's something going on there that is happening. They realize that particular data is going there is coming from a high usage traffic. So they might redistribute that somewhere else in the data center. And they're using soft switches. They're not physically moving these machines around. They're moving how the work is being done. And another one that is probably pretty important is genomics, bioinformatics. If you see this red-green cluster here, it's a particular scan of DNA, and they're trying to match DNA and group individuals by genetic similarity. We're going to talk about a few of the unsupervised machine learning algorithms. Let's just real quickly, has anyone heard of association rule mining, clustering, k-means algorithm, principal component analysis? We'll go through these in more detail. So the first one is association rule mining. So what does that mean? So imagine I'm collecting information and I see that a customer comes out to check out line in a grocery store and they buy bread and milk. Another customer buys bread, diaper, beer, and eggs. Another customer buys milk, diaper, beer, and Coke. Bread, milk, diaper, beer, bread, milk, diaper, Coke. And what that does is like they see that if I tend to buy milk, maybe I tend to buy bread. So there's a correlation, meaning that if someone tends to buy milk, they might tend to buy bread. So that's one way of grouping. And then the other one is like, oh, maybe if I buy a combination of diaper and milk, I might be buying beer too. Now, can you imagine why that's happening? Why would I buy beer with diaper and milk? You can only guess there, but I'm assuming that maybe someone after taking their baby, they might need to drink some beer, but I'm just making a joke here. But the idea is that you see a bunch of data that tends to show up together. There's a tendency for some sort of relationship. So that's called association rule mining. It's by association between different things that tends to show up together. Any questions about that? Is that clear? Nothing confusing about that. It should be a pretty relatively simple concept. The next one, so here's an example. So you've seen association rule mining at work. How many of you use Facebook on a daily basis or Instagram or web browsing, and you see all these ads pop up at you? Haven't you noticed that once in a while you will look at one site that you happen to go to and accidentally go to, and you're like, oh no, that's not what I wanted to do. And then for the next 5 days, you're just getting ads about that one thing. That's just bad application of associated rule mining in some cases. But for example, some of us will watch a video on YouTube. And for example, I'd like to, watch top 10 best Mac OS tips and trick. If I'm a big Apple fan, I'll watch something like that. But at the same time, YouTube will not have these ads unless you pay for it. YouTube will have these ads, and you'll notice they're trying to sell you some, I don't know, new mouse or new keyboard cover or just some power bank or something with that. So based on your viewing, based on how you look, these companies are using some sort of association rule mining to kind of match up what kind of ads to target you. We're going to talk about a bit of clustering. So there's two types of clustering. One is called hierarchical cluster analysis, HCA. And the way it kind of works, there's two approaches. There's a top-down and a bottom-up approach. Top-down is it starts takes a big cluster and starts dividing them into pieces. I don't want to say it's like a binary decision tree, but it's kind of like a tree that goes down. And at some point, you break the cluster based on, let's say the cluster is red versus blue, and you're like, okay, we're going to break it by red versus blue, and it's going to go there. And in the red group, it's like, okay, small and big, and it breaks apart, small versus big. And likewise on the green side, blue side, you're going to do something similar. And it just starts breaking them into smaller groups and smaller groups and smaller groups. That's top down. From bottom up, I start off with many different little groups I might have, and between the little groups, I say, oh, okay, these bunch of, for example, beans has the same color as this other set of beans. Maybe we'll lump them together. And then maybe this new group of beans with the same color are the same size as these other things, and then lump it up. So from bottom up, it's just combining commonalities upward. The other one that we'll talk more about is partitional clustering, specifically one called k-means. And we're going to go into a little more how k-means works. So imagine you got a bunch of data. Imagine you have all these dots, blue, red, and imagine that there's no colors whatsoever. And what you're going to do is you're going to pick a k, which is the centroid, and you arbitrarily pick them initially, and let's say you put it here and there, and then once you pick them, you're gonna look. Let me annotate actually. That will help. So let's say you pick a point here and a point here. What you're gonna do is like, okay, now I'm gonna look at all these other points and pick the ones that are closest to that point, and the red ones get here. What happens is once you start picking them, you're going to let's see if I can. And then when you find the initial set, you're going to move your centers to a different point. So for example, now you have all these points here, you're going to move them because the center is not the center of your group anymore. So you're going to move it based on what you're going to move your center from there to there. And in this case, the center here might not have moved much, but it's going to move it again. And then you're going to repeat. You're going to then say, what are the closest points that are closest to the center that I've picked out? You're just going to repeat this process until you're going to eventually form natural clusters in your data. And what's going to happen is that center is not going to move a whole lot more. It's going to pretty much, you're going to repeat this until that center just basically converges and your groups don't move a whole lot anymore. You guys get that so far? Like basically I'm picking points initially. I'm going to assign the points that are closest to it and lump it together. And then after that, I'm going to find a new points based on what is the center of that grouping, move my center to the new grouping center, and then start looking at the points again to see has any of the points changed with regards to its grouping. It's a nice video we'll show, kind of give you an idea of how that iteration, if you were to program this out, how that would look like. So let me I'm going to pause right here. Can anyone explain what's going on here? Well, what are you guys observing?
For each group, one of the points was selected, and then it's moving closer to the center of that cluster, and it's like changing the points around it to match the color of the center.
Yes, that's correct. Do you know why it's changing colors?
It's the color of whichever center it's closest to.
Yes, that is correct too. There we go. Does this video help you guys understand what's going on? Okay, cool. So question here. If you were presented these objects, how many clusters do you see here?
There's 6 different objects unless you like kind of take the blue ball and the blueberry to be one object.
2.
2? Okay, we got 6, we got 2.
I guess if it's by color, then there's 3, like the red, the orange, and the blue.
Okay, anyone else would like to suggest how many clusters they see here? All very good guesses. Maybe 2 if we, let's say, lump all the round things together and all the square things together. Maybe 3 if we lumping by color. I mean, do we have 2 or 3 or 6? So part of it is just trying to, like when we're using k-means, we have to pick out these points, right? In order to find how many groupings we are. But how do we know how many points we need to pick? Could be 3, could be 2 in this case, maybe 6. Like you can pick, I could only have one centroid or one k point, or I could have as many as the number of points that actually exist. Like in the case, like if it's 1, there's just all objects, it's not going to tell us a whole lot of information. If we do 6, which is, it's also valid, it could be just 6 objects, but are we really learning any relationships between the two? So 2 or 3 would make more sense in the sense of if we're trying to find relationships, like in this case, there's a relationship between red, orange, and blue, or by shape. But this is a big question, like how do you know how many groups that you have, how many points you need to pick to develop those groups? So there's something called like an elbow method. And the way it works is, imagine that the pictures of the video we saw before, we're trying to find which points are closest to the center. And what we're trying to figure out is, initially, if we get the distances between all the points to the center and do a sum of squared errors, we're going to see that if it's not initially at the initial point, it's going to be kind of everywhere. And if you only have 1, you're going to have a lot more, the number is going to be larger. But as you start developing an increasing number of values of k or centroids, that distance will decrease on average. And then what you do is you can vary that by increasing the number of points or groupings that you have. At some point, you're going to realize that no matter how many points you have, you're not going to get a whole lot of advantage, or that number is not just going to get smaller that much. So basically, what you want to do is probably find the point where it bends the most at this point, which is in this case 3. You have 1 point, you have 2 point, the average distances, which is a sum of squared errors, basically in that form, is being minimized. And that's why this is called the elbow method, because in this case it looks like an elbow. It doesn't always look like an elbow. Sometimes a little bit more flatter than this. It's a bit of math, not a lot of math. There's a bit of math involved, but it has to do with the distance between the points of the data to the center of the center point that you've picked. And if you have more center points that you've picked and you're grouping them, then it can vary. So let's say you applied K clustering algorithm to these. Do you think it'll work well for these patterns of data? And just as a disclaimer, all the data we've been showing is 2-dimensional data. And each dot is a data set, is different data points. So if you looked at it, just pick one image. Don't look at all of them at once. Just pick one image and think if it will work for you guys, or if k-means will work for this.
It'll work for 3, but not for...
Why will it work for 3?
Because it goes down and then goes up.
How does it go down and go up?
It's like a parabola.
All right, so let me annotate. So I'm going to take your 3 example, okay? Let's say I pick a centroid here.
Mm-hmm.
I pick a centroid here. Where do I pick a centroid for this one then?
You can't.
Let's say I pick it here.
In the middle, like in the vertex, I guess, yeah.
So if I'm trying to reduce the distance between a data point to the center, is, let's say, a point here closer to this point here, or is it closer to that point there?
It's closer to the one in the green and the one in the red than the top one of the black one, so it won't work.
Okay, now, based on that understanding, everyone, which one of these do you think will work for k-means? So one of the key things is, with k-means, if you have data in a very symmetric pattern, it's not going to work. Obviously here, what happens with this is your point's all going to converge to the middle for this particular one. This one's just all over the place. It's almost evenly distributed across the two-dimensional plane. Same with this one. This one is just straight line, so it's very similar to the situation for 3. And 6 is pretty much a combination of 3 and 1. So that was k-means. Now we're going to talk about principal component analysis. And oftentimes we're dealing with a large number of data, and that data will have a large number of features. And if you try to plot those features, for example, let's say the house example we have what? The area of the house, or the amount of space there is, the number of bedrooms, that's already 2, number of bathrooms, that's 3. Anything else, let's say two car garage or 1 car garage, so garage space, that's 4. If it's 2 floors or 1 floor, that's 5. So as you can see, as you're plotting a particular category of something, your features can increase dramatically. Now, we're used to drawing 2D graphs, like an X and Y axis, right? To easily plot something. Imagine you have more dimensions. You have 3 dimensions, you could barely plot that. Imagine you have 4 dimensions, 5 dimensions, 6 dimensions. So on a computer, they could see that, but for us as humans, it's hard for us to envision multi-dimensional planes and axes. And so one of the things we can leverage is that some of features, or using the concept of relationships, correlations, are related to each other. And so, for example, I might tend to have a larger garage if I have more space on my land or for my house. So there might be a relationship that way, or more bedrooms or more bathrooms. It may not be directly correlated or related, but sometimes we can say, hey, sometimes these things are related. We can just use one of these in order to basically reduce it. PCA is basically you're picking out principal components or features in this case to do the overall representation. So there's a famous data set out there which is used in machine learning, which is based on the iris flower. And the iris flower will have the length of the sepal. Does anyone know what a sepal is? Or sepal, if I'm pronouncing it incorrectly. So a sepal is part of the flower with angiosperms. Usually green sepals typically function as protection for the flower and the bud. So sepal is that green thing that's right below the flower, okay? And where you sometimes they measure the length, the width, the petal length, the petal width. And what they did is they just kind of combined your 4 dimensions here to 2 dimensions. And that makes it a little bit easier for us to look at. And so the idea is that you can kind of plot your data in a certain way. And if you have another examples like the house example or some other examples, when you plot your data, you're basically, it requires a bit of matrix math to kind of look at all your data. But if you plot everything out, you're basically, let's say you have a 3-dimensional plot, sometimes you rotate it. You imagine rotating a 3-dimensional graph, you might be able to see better axes and better groupings. So the idea is you're doing dimensionality reduction with PCA. You're trying to reduce the number of features or axes or dimensions, however it's being called, in order to reduce the number based on their relationships, so that it's easier to kind of look at the groupings and calculate the groupings. Another algorithm we're going to talk about is topic modeling. So for example, why would you do topic modeling? Maybe you're managing grants for the National Institute of Health and you're asked to sort out various categories of grants or the relationship among the categories that you're seeing here, or you're finding any influences from the main authorship. So at the NIH, basically you're going to get a proposal for some sort of research, and they basically try to give out grants based on those proposals. And when they're sending in the proposals, you're getting a pretty decent sized reading. And what you can do with that is you can use topic modeling to extract what are the main topics that are coming across from these documents. So for example, what you might see is some groupings. So this is like a grouping of data. Maybe you get a whole bunch that's related to cell biology. Some of it may be biological chemistry and macromolecular biophysics. Some of it regards to risk prevention, health behavior. So basically they're finding clusters, mappings of different topics that they're getting different topics from proposals that are being submitted to them. And how they're using that is something kind of like a bag of words. So I take a document, I'm going to strip out all the words from the document. I'm not going to care the grammar, if it's in the first paragraph, if it's in the last paragraph, if it's one of the 3 points it's making I'm not going to worry about positioning. All I'm doing is collecting words. And basically, when I collect words, I'm going to say, oh, it appears 6 times, I appears 5 times, the appears 4 times, whimsical might appear 1 time. So technically, it is a bag of words. There's no structure in the sense of ordering of the words. It's just a count of how many times the words show up, with disregard to sequence, pattern, grammar. Like in a particular proposal that you get, for example, at the NIH or National Institute of Health, yeah, you're going to get, a count of numbers, a count of words. And based on that, they're going to say, oh, this word shows up quite often, so that there must be a cluster in that. So if I see the word COVID-19, for example, then I'm going to say, okay, there must be a grouping for research papers that have COVID-19. It must be a big topic. Can anyone pick out the flaw with that? If I'm just counting the list of how many words showing up in a document, and I'm basing it by frequency of words, can anyone guess what could be a major flaw?
Yes, I, be, to, that kind of stuff.
Yep. And so imagine, am I going to have a bunch of research papers about it, or I, or the? So do you see that is a problem? Yeah, what about these words, the, it, of, a, and there's probably a ton of other words that are more popular than more specific words. So here's a rule you have to apply with the bag of words here. So if a word appears frequently in a document, then it should be important, and we should give those type of words a high score, which will indicate that grouping. But if a word appears in other documents too many times, then it's probably not a unique identifier, and therefore we need to assign a lower score. So does everyone get the intuition of that? So it shows up really highly in a document, but across all the documents that we're seeing out there, it's showing up in all these documents. So the commonality that it occurs in all these other documents, especially all of them, like you might have, I don't know, the word macrobiology show up out of the 1,000 documents you're seeing. You might see macrobiology show up in maybe 10 of the documents, but not to the state where I shows up or it shows up across all the documents. So there's some formulas that you apply here. So the first one is the number of times that a word occurs in the text or the document over the total number of words. So if I have a document paper that has 35,000 words, and let's say the word macrobiology shows up, 400 times, then you're going to get some value. Obviously, if I pick I, it's going to show up, or the, it's going to show up a whole lot more. But then what you do is you have to look at your total number of documents and the number of times the document with a word, say it, is in it. And then you're going to do some sort of calculation to figure out, okay, it's going to get a lower score. So this example, I'm going to be very bad with this, so I apologize. So consider a document containing 100 words wherein the word cat appears 3 times. So the term frequency, if we apply the formula, the cat is then like 0.03. In this case, it's a percentage, since it's very close to a percentage because it's 3 over 100. Now, assume we have 10 million documents and the word cat appears in 1,000 of these. So then you're going to do something called IDF, the inverse document frequency, calculate as the log of 10,000, is that right? No, 10 million divided by 1,000, which equals 4. And you apply the formula. The TF to IDF weight is the product of these quantities, which is the initial percentage within the document times the number of times that the document, out of all the documents, the frequency shows up, which is 0.12. That's pretty much all the algorithms we're going to cover for today.